with a company called Rocky Mountain Technology. We've been involved for roughly 16 years of providing technology solutions for engineering in high schools and colleges and community colleges. Anything from CNC equipment to laser cutting. This is a quick overview. Carl Thompson's my up manager at Stratasys, who prepared part of this for me, so he's in here. So here's kind of a breakdown of our company. We do 3D printers, laser cutters, desktop CNC, engineering software, SolidWorks, which is one of the premier ones out there right now. Mastercam. We do some Hampton training systems with electronics. Gary, you take this? It's Justin, he's on his way. And electronics training systems, virtual welding, and lots of lab furniture and furnishings. So doing this, we get involved a lot with a lot of universities that are doing research projects and doing oddball things. So this has been probably the most exciting 16 years I've ever had in my life, just learning about what's going on in education, because it's so broad. And we have 4 states we typically cover. We concentrate mostly over here in Arizona just because of the proximity, and it's a lot easier to manage. So moving along, we are going to kick off with a quick video, if we have sound.
This is just a quantum.
Kind of an overview of 3D printing.
It allows us to take what's on the computer screen and turn it into a real-life physical model in a matter of hours.
There is very much a wow factor.
Really changes the way we think about production.
Being able to make a difference and leave my mark is really what inspires me.
This is one of those industries that matches perfectly with 3D printing, additive manufacturing, because we need custom everything.
Client can come in and see that we're not just one of 8,000 processors, that we actually invested in technology that makes them better, differentiates us from everyone else.
Now we've got a 3D Fenway part. This came up from printer. Is that what you said? Believe it or not, it's a 3D printer that jets on resin that turns into a plastic when it's done. By having this 3D printer, we can have a very, very short turnaround time, more than any other company in this field.
You can rapidly prototype complex products without the need for the major capital investment in a production line.
The technology affords you the ability to actually get back one resource in this world you can't buy at this time.
It allows our students a lot more hands-on opportunities. They can take the object and they can test it, and you can see the theory being supported by the actual physical results. You know, that type of information is priceless. You guys are really on the cutting edge.
They can take it into the big boss at the company. Here you go, boss. We've got a great new system. We're going to sell 1 million of them.
There's really no words for me to describe how cool it is.
Stratasys is able to take a CAD file, we can import it into the machine and print a part in hours.
You can redesign the part to take advantage of what 3D printing can really do, which is very complex geometries that just can't be made by any other means.
We're working with Stratasys. What we're trying to do is take their technology and go from prototyping to real manufacturing. You can make parts, you can make systems that can't be made any other way.
This was a 3D printed model.
That is absolutely incredible.
Having this technology here was a game changer. It was the difference between killing a program and keeping it moving forward.
I apologize it being such a strong sales tool, but that's what it was designed for. But it gave you a pretty good overview of the main technologies that Stratasys encompasses in their 3D printing. And one of them is called PolyJet technology. The FDM technology is what we're using outside the door with the U-print machine. And we'll discuss this PolyJet technology shortly for just a short bit here. What PolyJet is, it actually has a print head. This print head right here is about 2 inches in length. So we're not getting a whole picture of the printer, which it kind of gives you that illusion. Within that print head, there are 192 orifices that are individually controlled that emit either a support structure, which we'll talk about in a little bit, or the actual photopolymer, which constructs the actual model. And basically when that runs, it's going to be going back and forth, dropping these droplets in here. The PolyJet systems, we'll go over some of the models here. The ones that you see have a real shiny surface and are very smooth. They're done on the PolyJet machine. They have real high fine feature details. They have maybe all the way down to maybe a 14 micron layer resolution. All of 3D printing, which is, by the way, we're going to talk a little bit about that bad word. 3D printing was adopted and then embedded, and now we can't get rid of it. It should be called additive manufacturing. That's the technical term for it. We're adding a layer at a time to create our model. But with the layer levels on the PolyJets are down to 14 microns, which is just about the size of Cherie's, the thickness of one of your hairs. So that gives you a lot smoother side surface finish. It's a pretty fast process because we're using inkjet technology, and you'll see a picture later on of a video how fast it does move across the bed to print your model. FDM technology, on the other hand, a little more crude, but it uses a thermoplastic, which these plastics are going to be extremely tough when they're melted together. So what we have, we had a piece of filament around here. We'll pass them around. That extrusion head up there is getting forced through it some of this, it looks like weed eater line. Envision that if you can. It's just like a, I thought we had that out already, but that's all right. And so it's going to force that weed eater line through a tiny nozzle, and then it's going to come out at a real small diameter. Gary, you can pass this around. This is what comes out of the machine. And it comes out at 312 degrees centigrade, very liquid, so it melts into the prior layer that it's being applied to. And each layer is about 10 thousandths thick, so you have some striations. You can rub your thumb on this and you can feel the different layers, but when you look at it with the naked eye, they're not very detectable. This gives you very good part strength and geometry accuracy with your model. Two other types that we don't sell are SLA and SLS. SLA is using another photopolymer, and photopolymers are typically cured with a UV light passing over it. In this case, they're using a UV laser, which is going back and forth rapidly on the surface of a photopolymer and solidifying the material on that layer. Then they'll bring in a little bit more fluid, raise it up by a few microns, and reapply the next layer with the laser. And before you know it, you have your whole model done. 6 or 7 hours for something like that. One of the most popular sintering systems, I think 3D Systems has, we're using a laser beam into a powdered nylon or a powdered plastic, and in some cases metallic materials to actually build something out of titanium. Gary will talk a little bit about the processes used for making medical implants out of metal and transplantable plastics for other bone structure. Any questions? So with stereolithography, you can get some pretty fine detail. You get a good balance of speed and surface finish. I'm just not sure. There are some support structures we're going to talk about that are made of the same material. You got to break them off and sand them down till they're smooth, but that's usually just called post-processing. With selective laser sintering, any of the powder that isn't turned into a plastic and melded to the prior layer basically can be brushed off with a stiff brush. So the post-processing is a lot easier, but it's very powdery and has a lot of issues with you need a good air system to filter that out with. It does have very, very durable parts. We've seen some parts as big as complete aircraft doors being built. And you can glue these parts together and sand them down. They're just incredible. Some of these machines, you might be able to fit 2 inside of this room. They're nitrogen backfilled, especially the powder ones, because you got a real hot laser shooting into a powdered environment, and there's a lot of airborne activity in there, so they have to be backfilled with nitrogen so there is no combustibility there. So that being said, there's 4 systems there, and I think we have another video to look
Standing
at.
on the shores of the Ohio River, cruising north into a quiet night in Cincinnati. The construction of the Civil War relic symbolized the dawn of a new age for the United States, bridging the geographic and social divides of the Confederate South and the Northern Union. By the turn of the 20th century, the Queen City of Cincinnati had become the matriarch of Western design, inspiring world-famous imitations from the Empire State Building to the Brooklyn Bridge. To most, this region is better known as the birthplace of aviation, and since the Industrial Revolution, the visionary designs of Cincinnati's best aviators and architects relied on subtractive manufacturing machines like mills and drills to cut those designs to life. But today, at the world's #1 manufacturer of aircraft engines, 3-dimensional design tools have exposed the limits of those 20th century manufacturing models. So what's being done to bridge the gap? In an ironic twist, it's here, in the fossilized outskirts of Cincinnati, where GE Aviation is printing a revised edition of its manufacturing rulebook.
That would be laser sintering into a metal powder.
We call it additive manufacturing, a 3D printing technology that allows parts, once thought impossible, to be grown from the ground up.
I think what additive gives us is a whole different degree of freedom on how we think about component design. We no longer have to understand what the limitations of machining are and what the cost of those limitations are. So now we've taken many of those processes and been able to kind of blow them out with additive. That gives the designer a whole different palette of colors to take on, and truly on a whole new canvas.
Since 2003, GE Aviation has tested engine components manufactured by an additive process called direct metal laser melting, where the guts of a solid metal part are grown from the ground up by a precision 200-watt laser. Those lasers melt together individually designed and ultra-thin layers of powdered metal until the part is fully grown.
What's pretty exciting for the additive technologies is that we believe we have the capability to produce components and alloys that would be very difficult or impossible actually to produce traditionally.
One problem additive solves is fuel nozzle coking. Traditional fuel nozzles spray fuel into the combustor at temperatures as hot as 3,000 degrees. Over time, carbon deposits form on the inside of the nozzle, degrading the efficiency of the fuel spray and the engine's durability. GE's additively manufactured fuel nozzle for the LEAP engine is grown with internal support ligaments and cooling pathways designed to eliminate fuel coking, making the part up to 5 times more durable than its machined equivalent.
Our work with the fuel nozzle has been really groundbreaking. If we can take a component, redesign it, even if it's non-traditional in its appearance, that potentially could allow us to save tremendous amounts of weight across multiple components on an aircraft engine.
What was once 18 parts is now one single piece, making the additive fuel nozzle up to 25% lighter than its predecessor. 19 lightweight additive nozzles will be installed in every LEAP engine we build, resulting in significant fuel savings.
In many regards, we look at this technology as replacing, in some instances, traditional technologies like castings or machining, brazing, and welding. One of the exciting parts about the technology is we can combine multiple components that used to be brazed or welded together and make them into one single complex unit.
By 2020, GE Aviation will manufacture more than 100,000 additive parts for the LEAP and GE9X engines. In the next 5 years, GE will invest more than $3.5 billion in new equipment to produce advanced components, like additively manufactured blades and blisks. To meet its record production backlog, GE Aviation is developing ultra-powerful laser beams and built-in inspection processes that could increase additive manufacturing speeds up to 20 times faster than what's possible today.
It's really remarkable, and this is just the beginning.
We've just begun to touch the surface of all the potential applications that we envision additive will be able to be applied to in the future. We're talking about multiple components, multiple different alloys, and many product enhancements that we believe in the next 10 to 20 years will quite honestly revolutionize the way many parts are produced for components going on the gas turbine engines.
For generations, locals have hoped.
Okay, we're going to move along here real quick because we got a couple other speakers that are going to be dazzling you with some really good stuff in the medical area. So even though the machines are only producing plastics, it's good to remember that on the thermoplastic side, that's the FDM strategy that we have out in the library there. You're going to get some extraordinarily durable parts, and other material properties such as polycarbonate can be run through some of the more advanced machines, which is a lot even stronger than ABS would be. We also have some high temp materials that are FAA compliant for smoke and flame that can go right from the 3D printer through inspection and right onto an aircraft for non-structural parts to be replaced. Bezels, air ducts. We saw an air duct down in Tucson that was about this big, that was printed on one piece on a 3D printer, and the company down in Tucson was paid $44,000 to print this one piece of piping. It would have cost Boeing, I think, somewhere near $150,000 to have one turned out of a single piece of aluminum. On the photopolymer side, we don't get to the high strength area, and we also have a kind of a high temperature issue where the materials might soften up a little bit. But as you have probably checked and picked up and felt some of these parts, we do have flexible capabilities. We have transparent capabilities, and we also have wild color capabilities in the photopolymer, which uses that inkjet technology to get that job done. There's some other examples of some ergonomics and things like that. This picture right up here is actually, I think it's used in, I don't know if it was BMW or not, but they were trying to build an apparatus that would assist assembly line to pick up a part and give them a little extra reach before they can nozzle it in or place it inside the engine compartment. And it saved a lot of pain, saved a lot of health issues. And the good thing about that, they could go back to the CAD drawing and make that just a little bit different, improve on it in just a few minutes and come back out, print one, and try it the next day. So for tooling, form, fit, and function, 3D printing has always been a pretty good avenue to take as far as giving you the edge. We're going to move on down here till we get into, I'll see if this is, oh, this is a good one.
He does is My name is Jason Lopes. I'm the lead systems engineer for Legacy Effects. What Legacy does is character design, creature design, suits, props, animatronics, and collectibles. 5 years ago, we realized that we really needed to change the way that we do things, so we decided to see what was out there for us to enhance what we do traditionally. And we had known about 3D printing from the early days. We even used it in the early days, but not to the capacity that would change our business or how we would do things. So when a special project came in, we did a Halo commercial. We figured it was the perfect opportunity to see what was out there and how it could complement us. So we started learning about object technology through a really high volume project working with a service bureau. And that was our stepping stone. Once we got through that project, we knew the technology was for us. One of the main reasons why we chose object technology was because we didn't want it to just do one specific thing. We wanted something that would be versatile, something that we could use for really high-end collectible maquettes, and then something that we could also use for specialized builds to actually put right onto people, and something that would also give us a choice of could we do things in clear, or could we do things in a rubberized material. And as far as what was out on the market, Object's the only company that had versatility for us. What we're seeing more and more now is that just besides building suits and doing hard surface things and collectibles, we're actually getting people coming in that are costume designers or makeup artists and saying, it would be great if we can incorporate this digital design into our costume design. Are you guys able to do that? And with the wide range of materials that Object offers, there hasn't been a job that we've turned away and said isn't possible. All that detail that people are seeing on a monitor needs to come through on the print. So our main thing is detail. What you see is what you get. What someone signed off on has to be represented. Our second thing is we're very versatile with this technology. We don't just use it for maquettes or just little characters. We actually use it on people, full 1-to-1 scale parts of body armor, things like that. So being able to have a strong part that'll be able to take some heat and take up to the process of molding and being able to really come through to create our volume amount of parts is essential. You know, a great example is, you know, there's many times where we think we have a locked design and we're ready to go, and at 4 o'clock on a Thursday evening, we'll have a revision to do for a client that they want to see immediately so their client can sign off on it. And I don't think there's any other way besides using technology like this that you'd be able to meet those demands of today's customers.
And next we get into the most recent release we've had in our capabilities is actually doing some multicolor parts, which you can see several of over here. This was a release last year. We have another speaker, Justin Ryan, sitting in the back, who's eyeballing one of these units for his for doing their research over at ASU and Phoenix Children's Hospital. I think that's with PCH. Okay, so we're able to print plastic high impact colors, not just dull looking things. Most of the powder printers that allow you to do any kind of color printing, it's got a powder surface. It's just not going to be as resilient. It requires a lot of sealing and sanding before it can become visible. Still works good. It's very efficient. Powder printers work fast, but the parts are brittle and hard to handle, especially when you get into real fine features. We're going to skip that one. We've talked a little bit about jigs and fixtures, and we're going to pretty much end this here in a minute, Gary, so we don't need the rest of the 40 slides. This is a list of materials that we're capable of doing in a lot of the other machines other than the one out there. So we have more advanced machines that have capabilities with higher temps. Polycarb ABS, PCI ISO for biocompatible, Ultim 9085, which is that high temp material I mentioned earlier that can go right onto aircraft. PPSF, resistant thermal and chemical. That part up on the right, we have a copy of that part around here somewhere, but it's actually fuel resistant and it can go right into a system that's going to be used for testing and if it's going to fit before you go to production. So it's very important to remember how well the printers fit into prototyping and getting your first articles out for proof of concept. Another benefit for some of the advanced machines are, if you've noticed, we have a part, those two red parts there, Chip. One of them is, they were both pulled off at the same time, but one of them, it had the support structure, which is the white material, the waste we call that helped hold that form in place. That is washed away in a detergent bath. It is not geometry that was created by the CAD drawing, but scaffolding that was created by the software. Now we have the ability to create geometry in a CAD drawing and just build that soluble support design so that you can use that as a mold layover for carbon fiber, or you want to do some polyurethane molding. So things like that. A lot of things changing in the technology, how it's going. Our four basic technologies we talked about are pretty much set in stone. Now you got SLS, SLA, FDM, and PolyJet. The big thing that's changing now are just the types of materials that you're able to go ahead and pack through these print heads and nozzles. So it's a materials race that's going on between the three big makers of 3D printers right now. All right, I think we're going to end this one here. And I'm going to go real quick over some dental applications, and then we'll turn it over to Gary. So we're Stratus, we're a big leader. Okay, so anyway, we get into kind of a workflow process. You got 3 CAD file. You need an STL, which a lot of CAD files are producing. I'm not sure how the file formats are figured in your proprietary software, but there's probably a good way to extrapolate either a Vermal with color or an STL file. You slice it and you put it in the 3D printer. So we're going to kind of flash through some of this. This is a representation of how that PolyJet still works. It's emitting model. You got the tray. A little complicated looking there, but we want to get to what we show, the pictures of the models that we have several pieces of over here, the medical and the dental. And just what we're looking for is coming up here, I believe. So we have, I guess you know what the glide well system is? Anybody on the dental side? Doesn't sound familiar? Okay. He said that, yeah, the guy who prepared this for me said you guys would know that, what that would be, but you might be wrong here. Anyway, for what a typical, this little illustration here kind of corny, I thought, but it makes sense when I went to the next slide. It says when you're in a dental lab, it's kind of an artistic gift to be there to be able to do things in a dental lab. So everything's going to come out according to the artist or their interpretation of something coming in. But when you get into the digital world, everything's going to be pretty much on a baseline of quality or consistency or accuracy. So when you're in the digital world and you can capture some of the data that we have in here, everybody's probably familiar with this. This is a manual impression, which you're using some liquid, I guess, to put in someone's mouth and get the impression. And now you guys, I think, are in Omnicam, the Sirona. So you can get a digital picture. And now we have this kind of a workflow. We have a capture. We can build that second tray there in the thing from your data, your CAD data. And you go into your design phase, you inspect, and then you can go ahead and produce either your blank or your wax or whatever you need to go ahead and prove that fit before you go ahead and create a tooth and drop it in and do all that. If you've taken the time to see some of the other models out there, some of those are a bit out of my pay scale. They might not be out of yours, but you can see some drill guides, orthodontics, all that. These are all done on 3D printers now. There is a specific one made for dental that runs a material called Med 610, which is good for about a 24-hour exposure. You don't want to permanently implant it, but it's a good way to do some fitting of orthodontic solutions or guides or anything like that. Do you have any questions here at all? Nope. Okay. And having seen these, they might show some value for you better there. And this is something that can be done with wax. You can go ahead and create wax patterns to go ahead and have casted into these apparatus here. And that would be it for me. And Gary, you want to? There we go. Want a pointer?
Sound okay back there? Yes. Hi, my name is Gary Harris. I represent OrthoSculpt. I wanted to give you guys a quick flyby on orthopedics. I know we have represented here dental, or the dental college, the PA college, and DO college. Perhaps some of the other disciplines are tuning in to the live stream. I wanted to talk briefly about what additive manufacturing can do for the orthopedics, or is doing for the orthopedics industry. This first slide shows how much money is out there in orthopedics. Some of your graduate students may decide to go forward in some of the surgical disciplines, and orthopedics is certainly a good one to go into. In 2012 in China, $1.7 billion was forecast in orthopedics alone. This first slide shows kind of the breakdown. The next slide will show some of the amazing acquisition activity that's been happening in the orthopedics industry. You look at 1998 for Johnson & Johnson, they acquired DePuy orthopedics. And a small note right there, you'll see that DePuy had 11,000 lawsuits pending regarding one of their total hip solutions. And still Johnson & Johnson wanted to acquire them. You go, well, why is that? Wall Street was scratching their heads, but DePuy has come out of that and relatively on the top. They became the largest orthopedics company. And then, not to be outdone, Stryker purchased Halmedica and Pfizer for $1.65 billion, mostly for their war chest of FDA, 510K submissions, and pre-market notification submissions. So they wanted that war chest of patents, if you will. And then now we come up to 2012 and we start seeing a stunning amount of orthopedic activity. And you'll notice that the largest was J&J when they bought Synthes. Johnson & Johnson now owned DePuy and Synthes. They call it DePuy Synthes. They bought them for $20.2 billion. It was the largest acquisition ever in the medical field. And then, not to be outdone, Microport, which is not even in orthopedics, decided to buy Wright Medical for $290 million cash. Stryker, SBI, they purchased them for $375 million cash. Smith and Nephew purchased Arthrocare for $1.7 billion, and then Zimmer, not to be outdone, bought Biomet for $13.35 billion. You'll notice over here, one of the reasons why they thought it was attractive to purchase these companies for such stunning amounts of money is because they have PSI engineering capabilities. PSI standing for Patient Specific Implant. We're all familiar with, if I can come over, we're all familiar with what would be referred to as a serial implant. Femoral head, femoral stem, implant, total hip arthroplasty. I stand here today in no pain because of people like you training surgeons. I have bilateral total hip arthroplasty, both hips. So I'm walking around with about 6 to 8 pounds of Stryker cobalt chrome. It's because of you guys and training students to go out, or doctors to go out and perform surgery. But what is the difference between a serial implant and a patient-specific implant? Patient-specific implants, it's an elegant new solution using additive manufacturing that Terry talked about, where precision anatomical defects can be corrected using state-of-the-art materials. Nowadays in orthopedics, it's mostly titanium, Ti64, cobalt chrome, PEEK, and PEC polymers. Put this slide in. We hear about the marvels and the miracles of 3D printing or additive manufacturing, and you hear about it more and more and more. Is it the end all? I throw this slide in. Can PSI engineering take a patient from this to this? Any thoughts? Creation of a craniomaxillofacial maxillofacial anatomy using donor digital DNA from a sibling. This is a patient last year in China. Born with congenital defect, entire craniovisceral anatomy is recreated using one of her siblings' files. And I'd like to talk about the value chain on how you do that. It'll be a quick flyby in orthopedics. Justin will do the same in cardiovascular space. Here's a serial implant. When I had my hips replaced, the surgeon most likely had my x-ray up on the box, light box on the wall. The Stryker rep came in and he had templates, and he basically held up a template to decide which size hip implant is going to pound into me. That's a serial implant. It's a quick and an easy way to replace anatomy that doesn't have specific anatomical requirements. PSI implants, or patient-specific implants, here's a case where, what if you have a lateral blowout? say a soldier is shot in Afghanistan. This is the lateral inferior orbit, maxillary and zygomatic arch with temporal blowout. What if the anatomy is not there? It's just shot away. How would you replace that? This right here shows how a patient can be CAT scanned, and that data using CAT scan and new technologies and software, we'll talk about that in a moment, and create an exact anatomical replacement. In the case of anatomy that is gone, what you can do is you can actually import the CAT scan of the entire cranium, and then where there is good anatomy, you can bring it in, because our bodies are chirality, handedness. There's left-handedness and right-handedness. If I have a lateral blowout on the right orbit, I can import that data, the CAT scan, and in the tool I can take it and mirror it, and I can digitally stitch in where the surgeon is going to surgically stitch in a new prosthetic. This is basically the PSI engineering process flow. You get the CAT scan, you take a 3D analysis of it, and then you render the data. I wanted to show you right here. Here's a CAT scan of a woman's hand, and you can see the entire point cloud, what we call the point cloud, all the way from soft tissue to the bone. So if you look at it from a cross-sectional view, you'll see soft tissue. It goes right up to cortical bone, then cancellous bone, then back to cortical bone, and then soft tissue. A surgeon can take and print with these technologies an entire model of their patient.
So you took the DICOM CAT scan file and had to convert it, or?
Yes. Okay. Yes. So what you do, and here's the process flow for DePuy Synthes. I don't know, can you see that okay? Or is it a little bit fuzzy?
It's pretty small.
Pardon me?
It's pretty small.
It's pretty small? Okay. So basically, go ahead.
That value chain before was pretty similar though.
It's the same value chain. This is the process flow for DePuy Synthes. You take the CAT scan data and you render the data in a usable form. And I have a little video clip that will show how this is done. This is the Mimics Innovation Suite software. You can see that you have the CAT scan represented in 3 fields. This is the superior, this is the posterior, lateral, and then a frontal view that is basically rendered in what we could easily identify. Now, the thing that I want to show you is right here in the bottom right corner. This histogram is basically a chart of this anatomy. Now, this peak right here, you'll notice this patient, does it look like they have a tooth in their body? They don't have a tooth, do they? So obviously this could be a reconstruction. You go up here, this is an army. You see army in the patient's name, but there's not a tooth in their body. So why is there a spike here? There's probably a screw somewhere in his cranium, somewhere, either in the craniovisceral or cranial-neural space. But what happens, and to answer your question, when we render the data, this histogram, we can slide this line back and forth, and we get to cortical bone, which is really what we're going to replace. We can then, and as you slide this bar over the histogram, you can actually see the data in the 3 fields change, going from soft tissue, and this is part of the point cloud, that soft tissue right here. And then if you could see real close, right in here is cancellous bone in between both sides of cortical. Can you see that? Let me go forward. We'll play a YouTube video on this, and I will be stopping to make a couple of comments. Again, Materialize, I have a relationship with them. So the first software tool set is the gantry and you're getting your CAT scan or MRI data. And incidentally, this is for a transforaminal lumbar interbody fusion repair. Here's our 4 different fields. They're taking the CAT scan data. So you import. Here again is the Mimics Innovation Suite. And you'll see, again, here's that histogram, and they're going to start driving. Here's all the 3 planes of the anatomy they've scanned. So they've created the model to say, this is the 2 vertebrae, L4, L5, I don't know, L3, L4. They say, okay, this is where we're going to do the TLIF, transforaminal lumbar interbody fusion. So they pull that out. Place landmark and watch here what the explanation of the operation is. And this will be interesting to your students or your graduates that do go on to an orthopedic discipline. Okay, FEA pre-processing. Watch the notes on the bottom. You see how this data is pixelized? It's actually not pixelized, but it's voxelized. In 3D printing or additive manufacturing, you need voxel data. We're familiar with pixel data. For instance, in space, if I take 2 points and I connect those 2 points, I get a line, right? If I add a 3rd point in space, I get a plane. If I add the 4th point, say like down here, I get a prism, or it's prismatic data. This is voxel data or prismatic data that is created through the CAT scan or MRI. What we've done is rendered that data into what is referred to as a watertight mesh. So now we can have a model. Once and to answer your point again, we've rendered the data into a voxel form. Once we have it in that form, we can manipulate it or edit it. So that takes the that's the second software suite, if you will. We'll export it to a 3rd software. So here we go. It's doing a density study. Now it's exporting to any tool. That tool could be Pro E. Justin, what do you use? You use 3-matic?
Abacus.
Abacus? Okay, 3-matic or Mimics, have you used that at all? Or SolidWorks?
Abacus gives us a bit more opportunities.
Okay. And so you do flow studies and fluid dynamics?
Structural analysis, medical devices.
Okay, very good. So that's what this tool is, an editor. Let's go on. Now the data is in a place where we can actually edit it. They're adding pedicle screws or pedicle alignment screws. Oops, went too fast. There's the pedicle screws for placement of there it is, the transforaminal interbody block. They're showing it going in laterally, mostly it's anteriorly. Sometimes they'll do a lateral transverse psoas approach. Hasn't been as good as the anterior approach. There's the block, it goes in. They verify the preoperative plan. Now enter additive manufacturing. You saw the DMLS, direct metal laser sintering, in the GE clip. This is what's happening here. And there's the preoperative model right there. The surgeon will actually handle that, say, yeah, this is what I got, and this is how I'm going to put it in. So that's the process step in manufacturing. Oops. Let's see, I want to go to... Here's an example of a mandibular reconstruction. I have an example that I designed with one of the engineers at Mimics. For those of you that do in the dental college for a mandibular reconstruction, especially in the case of, how am I doing on time? Justin, I'll give you, you're doing okay on time?
I guess so.
Okay. Here, when I was working in surgery, when we'd see a patient come in for a mandibular reconstruction, they'd go in, they'd pull the teeth, they'd incise the gum, expose the mandible, saw it out, sew them up, send them home for their oncology regimen. So they do chemo and radiation oncology. You see that same patient come back in, say, 4 or 5 months when they're done with their regimen. And then they'd schedule them again. They'd go in and they'd harvest a rib. So they'd harvest a rib, they'd put that on the Mayo stand, cut it in and segment it in an angle that would mostly approximate the data in the mandible that they were replacing. Screw it all in. It was about a 14-hour case usually. 2 operative sites. That's kind of the modality that was in the United States. In Belgium and Western Europe, they'd take a section of fibula or superior anterior iliac crest. Very painful. The next step in this reconstruction process, surgeons go, well, I don't want to do that anymore. So they devised a series of titanium serial implants. They say, if my margins are this far, then I'm going to choose a bar. If my margins for cancer are this much, I'm going to choose a titanium block this far. And so they would actually excise it, implant, sew up, done, send them to oncology. The end result for that patient would still be a denture. Now, in 3D manufacturing, you can actually take that anatomy as we've shown and you go, aha. You sit down and you do preoperative planning with your surgeon and you say, okay, I'm going to excise from here to here. He'll sit down with an x-ray and give you the CAT scan data. He'll say, okay, I want holes, attachment places right here and here. You'll notice in this model, you'll see right where all the vasculature and innervation comes through the mandible. Now you don't want to, even though you're terminating, what are the three nerves there? The trigeminal, mandibular, the alveolar, and one other. Which one? Those 3 nerves. You're terminating them, but you don't want to throw or plunge a screw into those nerves because they may be terminated here, but they're still up here. So these are issues you talk about in preoperative planning, but you can do anatomy that is exact. So you extrude this data and you have an actual titanium prosthetic that was developed or derived from the patient's own anatomy. So that's the beauty, and you'll notice here 3 single-stage dental abutments at the correct angle or the existing angle of the original molars. Same thing here. And that's a preoperative model that they actually had in surgery when they did the reconstruction on this mandible. I want to leave Justin some time, more time. Let me go through real quick. This is from OBL out of Paris. Materials science. One of the things your graduates, if they do get into this, is materials science. When you have titanium, which is the best material? Titanium, cobalt chrome, PEEK, PEC. These materials. So when you go and you send these materials to the lab to test them to get FDA approval, they want to test for genotoxicity, biocompatibility, bioactivity, in vitro cytotoxicity for morbidity and morphology, mechanical behavior, composites, You actually will put bacteriostatic materials right in the prosthetic. Beta tricalcium phosphate and that other stuff right there. The next thing is, and I really want to focus on this, bioactive and textured surface engineering. You can actually, the question is, can I create a nano surface for an implant that is good for osteocyte generation and ingrowth, and yet be bacterial prophylactic? In other words, can I find the sweet spot where if I have the prosthetic, where's the sweet spot so I can have ameloblasts grow in it and bacteria films not be generated? Amedica, which is a spinal company up in Salt Lake, is doing some of the great pioneering work in that. Here's an electron micrograph. You'll notice right here, that says 50 microns. Terry, when he was presenting, our machines are capable of 16 micron print fidelity. So here's 50 microns right here. This is some of the implants. A new material, silicon nitride. Amedica out of Salt Lake is the only company using that. Here's other micrographs on nanosurfacing and that technology. Your graduates, if they do go into surgical disciplines and they get into implantation, these are the things that they'll need to know. Here's biofilm studies for different materials: titanium, cobalt, chrome, PEEK and PEC, and silicon nitride. And you'll notice down here, A and B, the different bacterium that they're testing for. C and D, E. I'm done. Any questions? Terry's going like, Justin, come on.
Cost. So the titanium implant versus...
Great question. International ICD, International Classification of Disease, and CPT codes. The FDA owns the CPT codes. These insurance companies, I guess.
American Medical Association owns it.
Yeah. And FDA they will sue you if you post them. So the question is, how much does it cost? I actually sat down with Dee Whittingham of Banner Healthcare to hammer out cost. And she had no CPT codes at all. And in fact, this technology is wide open to your students. Their Banner had not had one PSI implant come in to their entire network as of the date that I talked to them.
Yeah, the insurance company pays the same amount regardless of how you fix.
Yeah.
The integrate.
Yeah, so the CPT codes are not defined.
So they don't care if you use a $5 device or a $50 million device.
That's what I was there to hammer out with them.
Device since you make profit on that.
Yeah, that's what I was there to hammer out with him. You sit down at the bargaining table and you actually hammer out what it will cost. Now Justin's going to go over cardiovascular, which is really interesting as well. Thank you.
Should I copy the hard drive first, or is it pretty good to run? That seems right. All right. All right. So I'm going to give you a little bit different perspective. I am over at Arizona State University. My name is Justin Ryan. I work out of the Image Processing Applications Laboratory, but we also have kind of a satellite lab over at Phoenix Children's Hospital. So we've directly implemented a lot of these 3D printing technologies directly in the clinical environment. At any point along the way, feel free to ask questions. So I'll jump right into it. I'm presenting this from a different perspective for vascular, so I'm going to give you some terms to make sure we're on the same foundational level. What I deal a lot with is cerebral aneurysms. So those are aneurysms related in the brain vasculature. Now, if you're unfamiliar with what an aneurysm is, it's a dilation or a ballooning of a blood vessel. Now, we suspect that this is up to 5% of the population has an undiagnosed aneurysm. So a very high percentage. We want to figure out how to best treat it. If an aneurysm ruptures and it's located in the brain, it's almost a 50% mortality rate in the first 30 days. So very serious condition. One way to treat it is endovascular. So that's actually threading a device through various arteries all the way up to the target location and deploying a device within the vessel itself. Seen here on the illustrations are two methods. One is coiling, which is this top one here, which you actually pack the aneurysm full of these tiny metallic coils to prevent any more blood from going to the aneurysm. The other way, here is a stent. So it's a kind of a metal mesh that goes inside the parent vessel, tries to divert flow away. There's flow diverters, which are very similar to stents, but much more metal in terms of the coverage. So looking at all these, we want to ask, a physician, how are they going to choose between these three basic options? But even among these three basic options, there's many variations of these types of devices. There might be coils that have a larger diameter or smaller diameter, bigger or lower length. These stents have different cells to them. So this kind of crown shape here, they can really vary from one stent to another. Or that metal coverage that I talked about. And right now there really isn't a set way that physicians choose between these various options. A lot of times it's by their training or by the vendors that are available to them. But we want to change that. As a biomedical engineer, I want to make sure that a physician is making the best choice for the specific patient. And that means understanding the hemodynamics, or how blood is actually moving inside the specific geometry. So to do that, we can do computer simulations. So we take a look at, in this case, a CT angiography image to locate the aneurysm. I've kind of highlighted in red here, and we do a patient reconstruction. So we reconstruct that data into a 3D computer model. Now what we can do from here, direct from here, is plug this into another system known as a computational fluid dynamics system. So we can actually run computer algorithms to show how blood is moving inside this specific geometry. Now with CFD, which is the acronym for computer fluid dynamics, it's really only as realistic as you program it to be. And that means there's a lot of deficits for a system if you don't completely understand it. So one way to test your computer algorithms is to relate them to an experimental model. So a true physical model that has the same geometry as your computer simulations. So if we start here with this three-dimensional model, we can go one step further. In this case, kind of looking at an end product, this is a urethane model of a cerebral aneurysm with actual patient geometry inside of it. So with this as the end goal, we recognized that we needed some type of 3D printing mechanism to achieve this very high fidelity model. Now, the current state of technology still has some layer striations caused by the 3D printing. So you see the tiny little ridges. And when we're doing something as detailed as something like this, those really do affect us. Plus, a lot of 3D printing technologies has some type of UV sensibility to it. And you'll see later part of our experimentation process utilizes a UV laser. So we needed to develop a process that we can achieve high fidelity that 3D printing delivers, but in a very different way. So seen here, this is actually a wax print of a patient geometry. If you want to pass that around. So we start with wax. We 3D print the wax, and then we go one step further and we actually cast it into a low temperature metal. So this is a eutectic metal. So it melts at about 212 degrees Fahrenheit. So now we're at a core model that represents the patient's geometry in a low temperature metal. We then encapsulate it in urethane. And then since it's low temperature metal, we simply melt out that metal from the urethane block, which is pretty much what you see there. There's some extra post-processing steps to make it as clear as it is, but that is what we achieve. Now the question is, what do we do with that? So here we have a picture of that cerebral aneurysm model. On the right-hand side, we have an experimental setup. So we hook this model up to a flow system, pumps blood analog through it that has tiny little particles in it. We shoot a laser plane through the model, hits those particles, they excite and they shoot off wavelengths that these cameras in the foreground capture. And these capture at 2 different frame rates. So if we have 2 different frames separated by a certain time, we can track those little particles moving and from there develop a velocity diagram of the actual blood analog inside this model. So we can plug in different treatment devices and see how blood is moving, how blood is being changed. Is there an increase of velocity, a decrease? And what's also seen just a little bit on this image here on the left, there's a little tap going in the aneurysm. So we also put a pressure transducer in there. So we can see how pressures are changing from different treatment devices. So now we talked about that correlation, experimental to computational. On the left-hand side is our experimental model, so a physical model that we've run through our system. Right-hand side, this computational fluid dynamic model. So we can see here in this one image, a qualitative correlation between the two. And from here, we can help derive those algorithms again. Maybe we can simplify our systems and allow us to run our computations much faster by better understanding our experimental setup. I'm going to be transitioning to another 3D print technology. Is there any questions on this kind of multi-step casting process? All right, I know there's a lot of information to absorb all at once, especially if you're not in the vascular realm. All right, so we talked about experimental. Now let's move a little bit into educational. There is a kind of scheme of education called medical simulators. So that's a physical model that represents anatomy and even physiology in some cases of an anatomical system that you can actually perform mock surgeries on. So as residents or even medical students need to advance their skills, we want to create models that are much more accurate than these kind of, not store-bought, but very generic models that exist out there. So in this case, we approach this through 3D printing. So here we have, once again, our 3D reconstruction of anatomy. On the right-hand side is actually 9 patients I collected, took out aneurysms from them, and overlaid them onto one single vascular tree. So this is known as the circle of Willis, if you're familiar with that anatomical system. We had to do multiple 3D printing steps. So in this vascular model, I wanted to include the skull, include the brain, and include the vasculature. And the goal here was to develop a surgical simulator. So in that first aneurysm segment, we talked about endovascular treatment. This one's going to be surgical treatment, in which you actually have to cut away part of the skull, reveal the brain, push it away, reveal the vasculature, and place a medical device on the vasculature itself. So a very complex system. We wanted to include all that in our medical simulator. To tackle the brain, we realized that currently 3D printing technology hasn't quite reached the elasticity that we want, something very, very low. So we needed to approach this from a casting perspective. We wanted the complexity that 3D printing provides. So we 3D printed different brain parts in the ABS plastic. We smoothed it out with some chemicals, and we took a silicone cast, which is seen on the bottom right here. So we took a silicone cast, and inside that mold, we casted even more silicone, a very kind of proprietary silicone that we developed. So a very squishy, compliant brain. The skull was 3D printed directly in a gypsum media, and our vasculature was printed in the objet printer, which allowed us to achieve a very low elasticity. In the case of hardness, we achieved, I think it was Shore A27 is what the objet? Yeah, Shore A27. So very compliant and just what we needed for this process. So here we have a close-up image. You can see how complex the skull is, especially by looking inside the sinus cavity. You can see all the trabeculae, or not trabeculae, the turbinates. We can see the brain being pushed apart, and inside there you can see just some vasculature being revealed. And in fact, we use this in an educational study to see how effective residents and students were at performing this mock surgical skill. So here they're using a bone drill to drill away the skull for craniotomy. They're revealing the vasculature and placing this medical device, in this case a surgical clip, across the aneurysm. So really what I wanted you to get out of this part is 3D printing can achieve a lot in terms of complexity and materials right now, but sometimes you can add an extra step, in the case of casting, to achieve even more materials that you might be interested in for your specific applications. But what I do a lot with is at Phoenix Children's Hospital, we developed a lab in the Heart Center. And this is kind of my baby here. This is what I do on a weekly basis. I print off heart models. So this is kind of the end result, but let's talk about the beginning steps. So at the Heart Center, there's congenital heart disease. So a structural malformation of a heart in which vessels might be missing or present or switched, or pumping chambers might be completely gone. Very complex, very patient specific. So we want to show doctors the heart before they operate on it. So what we do is we start with medical images once again. This is traditionally what doctors are used to seeing, this CAT scan image, this CT image, with contrast in this case showing different parts of the heart. With our current technology, specifically using the materialized mimics, we're able to capture three-dimensional volumes of that same anatomy. So very complex structures. However, if you're looking at this on the screen, it's probably spanning about 2.5, 3 feet tall. So you lose that absolute scale reference. But 3D printing allows us to print all these at actual size. Specifically, we use the gypsum powder media, so it creates these models here. If you want to pass around the smaller ones, you're welcome to. Yeah. So this is the end result of these models. So very complex structures. We can show very minute anatomy on these models. So I want to show a little bit of an impact story. I know probably not exactly what we're looking for, but show the impact of what this can do. This mother was pregnant. The child was diagnosed in utero as having congenital heart disease over at St. Joseph's. So on day 1 of birth, this child was taken, got a CT scan, data was sent over to me, I reconstructed the heart, printed the model, so the doctors had the model in their hand before the patient was ever transferred to our hospital. So they got to look at the very complex structures that you see here on the right-hand side of this patient-specific heart before the child is ever transferred, before the child ever set foot in the operating room. Very similar case here. This child has a very complex issue known as single ventricle. She also had a treatment known as Fontan, so a lot of different things happening here. She had a respiratory complication that needed treatment over at Harvard, but this patient was here at Phoenix Children's. We printed the heart. The family actually took the heart with them on the airplane and delivered it to the doctors that were going to operate on the child here. And now this has spawned a potential for a clinical trial with the same doctors over there regarding this 3D printing technology. So very high interest created by a relatively simple process. Unlike the casting procedures, this is almost a one-step process or a two-step. Medical images to reconstruction, then from reconstruction to 3D printing. Once again, touching on the educational part, over the couple of years we've had the lab over at Phoenix Children's, we've developed a library of over 150 hearts. Now each of these hearts comes from a patient, so each of these is unique to a child, and each of these means that the defect is unique. So we bring these over to U of A Medical Campus, we teach congenital heart modules, so we show the medical students variations of these hearts so they can see how a specific defect can present over a patient population. Last part is, this is why I was actually late today at a rush case. We developed a process utilizing just the 3D visualization technology, the materialized mimics, to do virtual implantations. Very quick background. Person goes into heart failure, they need a donor heart, but they might not receive one in time. So you can bridge that time between heart failure and reception of donor heart by using a ventricular assist device or an artificial heart. Now, I work in pediatrics, and most of these devices are meant for adult populations, so they have an inherent size cost to them. They may not fit inside the pediatric chest. But what we can do is we can utilize this technology to visualize in a much more detailed manner whether or not a device will fit. So here we have the patient's anatomy reconstructed in a very kind of crude manner because this was an emergent situation. We didn't have the time to refine it. But we have the different parts of the heart seen. We have the skeletal structure seen. And what we're going to do is we're going to perform the same kind of mock procedure that a clinician would do. So in this case, we remove the the bones to reveal the heart. We're going to remove the ventricles, so the pumping chambers of the heart. And now we reveal the rest of the vasculature that's remaining. And from here we can see where the valves will be approximately. From here we overlay laser scan versions of the artificial heart. And we manipulate them into place through clinician guidance. We place back on the chest, and now we're able to qualitatively see where the heart is overlying on current structures. So here we're looking at, once again, kind of outlines of the device on the current anatomy. So we can see that if this device was implanted in this specific patient, we're going to have a large displacement of lung, which is this kind of darker gray structure here. So utilizing both 3D printing as well as the 3D visualization tools, we can really open up our possibilities to pediatric care or even clinical care in general. I know I threw a lot at you there in a very short amount of time, so I welcome any questions either relating to the 3D prints or the visualization. For full disclosure, I'm not related to Stratasys and I don't have any stock share or anything like that, so feel free to ask any questions you want. All right, well, thank you very much for your time.